Like, because I look back at that handout we had the other day, I'm going to use it in a slightly different way. So if you don't have it with you, don't worry. I'm going to put it up here. And before I formally define any damn thing about continuity, I just want to see what you already kind of, your gut feelings about continuity. Right? I'm not talking about continuity amongst seasons of community or something, even though they are a good show for continuity. What the hell am I talking about then? No. We're going to come back to that. So, let's see. Can somebody shut off the one that says, I can't remember now, just experiment. Oh, right on. Sweet. We had a 50-50 shot. Alright, so I just want to look at this graph itself. None other question. We already answered all the questions. Where would you say this thing is discontinuous? Where would you say that this graph is not continuous? What point? Give me one point where it's discontinuous.
1 to 6? Or 1?
Yeah, at 1. Okay, so at 1, this bad boy is definitely not continuous. Let me just make sure you guys understand, because sometimes students focus way too much on the points that I just pick. What about at 2? Is it continuous at 2?
Yes.
Why?
There's a line.
Because it goes straight through it. There's no problem. And the really, really, really basic way to say it is I can draw through it without picking my pencil up. Right? Now this is obviously discontinuous. Right? And there's 3 main types of discontinuity. And you know exactly which one this is when I say it. So there's a removable discontinuity. There's an infinite discontinuity. And there's a jump discontinuity. And this one is definitely jump. I like it. Because it jumps from one place to the other. Right? Is that cool? I'm trying to come at the idea of what continuity is in a more, I hate the word organic, but just, we're going to flesh it out from behind. What else is it? Where else is it discontinuous? Yeah, 6 is discontinuous. Now be careful about this. What kind of discontinuity do you think there is at 6?
Jump.
It's called removable. It's not a jump discontinuity because the function doesn't jump. It's just a blip. It's not really defined where it's supposed to be defined. So it's called a removable discontinuity because all I have to do that is to fill in the hole. I can remove the discontinuity by filling in the hole. So people are trying to walk down a path and there's a giant sinkhole. They're going to go, holy shit. So to remove the problem, I can fill the hole in. Right? Are you guys kind of with me? So this is a removable discontinuity at 6. This is a jump discontinuity. There's no infinite discontinuity, but that's the one where you have a vertical asymptote, right? That'd be an infinite discontinuity. Is that cool? Yes. That one's pretty straightforward. It's discontinuous because it goes to frickin' infinity, so it can't connect. And what about back there? At -4, that would be another removable. Like if I defined f in -4. Now, here's the key thing. What would I do? I almost finished that thought, but how would I define the function? If I could define it one more way, it's defined up on the graph, blah, blah, blah. But what can I do for if x is -4? I could define the function in such a way so that it would not be discontinuous anymore. What would I say? What would I define to be true? How would I fill that hole in? I would just have to say what?
Why?
Is there an output at -4? Is there an output? No. What is that for the -4?
Undefined.
Beautiful. So let's define the damn thing so that the discontinuity is gone. How would you define it?
Y equals 2 and x equals -4.
So be more direct. F of -4 equals 2. I like it. Or you could say f of x is 2. Get out of there. F of x equals graph stuff. Or it equals 2 if x is 4. That's -4. Bam. So that's why we call it removable, because it's easy to remove the problem. We just have to fill in the hole in. This problem, I can't just fill in the hole and have it go away. That would make it not a function anymore. That sucks. No way to remove that problem. It's just a problem you got to learn to live with. How are we doing? What we just did will actually lead to the definition of what it means to be continuous, if we're careful about it. I keep taking a picture when I do that, I think. Oh well. I get used to that. Can you turn the light back up? Thanks, man. So what the hell did we just do? Why did that suddenly make it continuous? Why is this not savable? Not salvageable? Why is this one not savable, but that one is?
Is that point by itself?
What's the difference between these two things? What's the difference? Different functions. Now think in terms of the main idea we've been discussing. The limits are different. So the limit doesn't even exist there. Does the limit exist here?
Yes.
Totally. What's the limit at as x goes to negative 4? What's the limit? 2. Therefore, that's why it was an easy, and not more than just easy, it was possible to solve it. Do you guys get what I'm saying? So what does it mean to be continuous then? Well, the limit has to exist, but doesn't the limit exist here? And the function's defined, so not only does the limit have to exist, but the function has to be... No. In order for it to be continuous. So once we did this, wasn't it now continuous?
Yes.
And what is the limit at negative 4 as it goes to negative 4? 2. So we made the function value 2, right? So as long as the limit exists, so if the limit of the function exists, and that limit, we'll call it L, equals what? You can do it. So in this specific case, the limit exists, it's 2, and if only the function value at negative 4 was 2, which is the limit, then it would be continuous. So what does it take to be continuous? It's got to look like it's going somewhere, and it's got to actually go there, if you want to say it in less technical terms. More technical terms would be the limit must exist, and that limit must equal the function value there. Which inherently means the function value exists. Let me stop there for a second. I just wanted to really make sure that it made intuitive sense as to why we call that continuous. Because we could see how to make it continuous, therefore we should be able to define what continuous means. So really all this shit I put up here can be captured by just saying f of x is continuous at a if the limit as x goes to a of f of x equals f of a. That holds all this. I wrote this equals a number, so therefore that limit must exist. This equals this, so therefore this must exist, and they must equal each other. There's like 3 parts to this that this captures in one swell swoop. There it is. One swell fella. How do you guys feel so far? That's continuity. I've sort of already talked about it a little bit. And the reason I'm doing this section right now, before even talking about section 2.3 is, section 2.3 is going to make a stupid amount of sense once we talk about some theorems about continuity. Right, so here's continuity itself. That's what it takes to be continuous. Blah, 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 blah. Oh, we already talked about that. So there are a few important theorems in section 2.5. There. Back. Here we go. Theorem 7. Let me put it up here for the book list amongst us. Alright. So I want to ask you a quick question. The rational functions. Are there what's wrong with rational functions? What could be wrong with rational functions? Like 7 over x minus 1. What's wrong? Where's there a problem spot with 7 over x minus 1? Domain is limited. But all of these are continuous everywhere on their domain. Do you guys understand? Yes, so that's why don't freak out that some of these have problems on their domain. Right? They have to exclude certain values. But the function 7 over x minus 1 is continuous everywhere except at 1. In fact, what kind of discontinuity does it have at 1? If you graph this, what would you put at 1?
A hole.
Not a hole, no. That would be so bad. You only put a hole if it actually cancels. If there was that, then there would be a hole at 1.
There'll be an infinity.
Yes, if you graph this bad boy at 1, there'll be an asymptote like that, right? And up here it'd be, and then there would be, whatever. You guys understand?
Yes.
All right, sweet. But the important thing there is continuous everywhere that it's allowed to be continuous. Well, where is it not allowed to be? Anything not on its domain. So it's continuous on its domain. Every single function they list in there. That's step number 1. I'm trying to show you why 2, 3 exists. I didn't realize before how much I don't like the organization of this book. 2, 3 shouldn't have been put first. They should have put this section first. Because everything in 2, 3 comes out of what we're about to say. Theorem 8. So let's see if this makes sense. If f is continuous of b, and the limit of g is b, then the limit of the composite function is just f evaluated at b. So what's all that shit mean? We've already kind of done this. And I was sort of operating on... well, let's see if you guys get this. What would that limit be? 1. I love it. So some of you guys realize that it's only when there's a problem at the number I'm interested in that you actually have to do something weird, like multiply conjugate or something. You're trying to rearrange the function on the inside so the problem cancels. Is there a problem at 3? No. In fact, this function is what at 3?
1.
But broader. It is continuous at 3. I like it. Because it's continuous on what interval, this function? Who can get that? It's continuous on what function? On what interval? I love it. 2 to infinity. I like it. It's continuous on that entire interval because that's its domain. It's continuous on its domain. Let me stop there for a second.
Oh, okay.
Gotcha. So this is what we were talking about before because it just makes sense. But now I do want to come back and bring in some formality to this. As long as the function itself is continuous, you could just bring the limit inside. Which is really what that stupid thing is saying. I don't think you guys realize that. So what is my f here? So f of g of x, what's my f? What's the outside function? What's the outside function? The square root. So the f would be the square root, and the g would be x minus 2. I like it. Is that continuous? Hell yes. Is that continuous? Hell yes. On its domain, right? That's all that matters. Therefore, the composition is continuous. I'm actually getting a little, there's another theorem in here in a second that says that. But all this says, I really want you to see how that says the same thing that we did here. This limit is 1, because when you plug a 3 in, you get 1. It's continuous at 3, therefore the limit at 3 must equal what? What's the definition of continuity? The limit as you approach 3 must equal the function value at 3. And the function value of 3 is freaking 1. That's why I'm allowed to plug 3 in. Maybe. So in the theorem they say the limit as x goes to, what do they use? A of f of g of x. If f is continuous, you could just bring the limit in. Which is the same thing as saying you just plug an a in. Right? Do you guys see what I'm saying?
Yes.
So that would mean that this equals f of g of b, and they said that g of b, I'm sorry, g of a, sorry, we're doing it. G of a was b. That. So they're really saying the same thing of what we just did up here. All right, we really want to make sure you understand. So when you have a composition of functions that are continuous, you're allowed to bring that limit inside. Okay, cool, I like it. Good. Let's see, what are we? So here's the one I got a little ahead of myself on. Number 9 says if you have a composition of continuous functions, then the result itself is continuous. So the square root of x minus 2 is continuous because all of its parts are continuous. Is that cool? Okay, okay. Let that be nice. Okay. Oh, and Theorem 8 is basically where most of section 2.3 comes from. That's why they should teach this before they teach that. This is why section 2.3 is allowed to be done. So if you look back at section 2.3, and I'm not going to say much about 2.3 because there's really not much to it. It says all this can be done. So if you wanted to take the limit of a sum, it's the sum of the limits. You guys with me? And that only makes sense. If I want to know the limit of x squared, x goes to 2 of x squared minus x, what would you do? What would you do? Plug a 2 in. Where? In both. So what did you effectively do? You effectively took the limit to both pieces. Be careful, you didn't distribute it. I know it looks like you did, but you really didn't. You took the limit of both pieces. Is that cool? I like it. Good. All right. So that's all that thing. And you can see the rest of the subtraction is the same way. Multiplying by a constant. These are basically things that should make some common sense. That I should be able to do this. The limit of a product is the product of limits. The limit of a quotient, the only place it could possibly have a problem is if the bottom function is 0 and a. That kind of makes sense. Otherwise, it's just a straight up division. I like it. I like it. All right, good. All right, I don't want to make a big deal out of 2.3. You can read through it. You can bring back questions. 2.3 is not a big deal, especially if you learn continuity first. And the reason that these work, and then they go further, they have these specific theorems that you don't need. There's little things. You can pull the limit inside of an exponential function. Why? Because an exponential function is continuous. Do you guys see what I'm saying? So if you learn about continuity first, the section 2.3 is not even really necessary. You've already set it in the continuity section. There's an exponential, there's a root function, which is an exponential function, right? It's just a rational function, power. Radical stuff. You guys with me? Radical. Okay. Trying to get to the good stuff. So here's the good stuff. Just the really nice one. Something called the intermediate value theorem. And it sounds very difficult, but it's remarkably commonsensical. I'm going to continue to say that, even though some of you guys won't believe me. But just let me draw you a picture, and you tell me what you think. Not tell me what you think about my drawing, because I know what you should think about my drawing. Yeah, that's what you shouldn't say to me, because I know you're lying. I don't like that. So let me ask you this. Let me tell you, f of x is continuous, at least on a, b. Alright. So normally I'm going to draw a and b in the first kind of quadrant, but it's just one way to do it. Because a and b could both be over here, whatever. You guys with me? A is less than b, though. That's what that sets up. So here's a, here's b. My function is continuous on a to b. And let me just say that f of a does not equal f of b. Just get that out of the way. So f of a could be here, let's say. And f of b could be there, maybe. Sure. And you know the function's continuous. So somebody, so in between f of a and f of b, there's a lot of numbers, right? There's an infinite number of numbers. So let's say somebody wanted to stop. Stop. Okay. So this number right there, let's call it n. Why? Because I don't know what it is. I'm going to call it something, right? And I chose something before you did, so we're going to call it big old n. So here's what the intermediate value theorem says. Can n escape being an output of f? Is there a way to connect? So, is there a way to put this? I know the function's got to start here and it's got to end there. So the only possible way that it won't have an output of big ass n is if what is true about the function? What has to be able to happen? It's got to have a jump to it somehow, right? Yeah. It has to be discontinuous. But what did I say? It is continuous. Oh shit, so what must be true then? There must exist. What do you think we're going to call it? There must exist a point C such that f of c equals, I love it, n. I like it. In my head I had that scene from, what was that? Better Off Dead. Have you ever seen Better Off Dead? No. And the teacher saying all this weird shit and everybody's like, yes, and he's like, I have no idea. what he just said. So when I hear myself talk, I'm like, please don't feel that way about what I'm saying. This isn't that bad yet. Right? That only makes common sense. So some of you guys are like, that makes too much sense. I'm not going to say that. That makes too much sense.
There's a theorem for that. It seems so.
I know, but it's because it's not that obvious in weird situations, which is why you want this to exist, so you know that a big goal to be able to do a lot of the theorems that is built using this. This is like a basic beginning step to prove a lot of other theorems. So what do you want to know about your function? If you want to use these other theorems, you want to know that your function is continuous. Therefore, you come up with ways to test for that. You got it with me? And the functions we're going to use are going to be pretty basic. Whatever you feel about them, they will be, because you don't know what they could look like, right? But we have very simple ways to figure out if something's continuous for our functions. Okay, maybe. So I like what you said. This almost seems too easy to believe that it's a theorem, but it must be a theorem because it's not actually immediately obvious for some functions. But if the function is continuous, then this has got to be true. There must exist. Let me show you some this means there exists. A big old backwards E. There exists C element of A to B such that f of C equals n. All right. Just to make it sound worse than it really is, but it's not that bad. Okay, cool. I like it. So that's intermediate value theorem, the IVT. So what's an immediate use of the intermediate value theorem? You've used it already, believe it or not. Let me see if you guys remember this. I know this is a bad memory for some of us. Do you remember doing stuff like this in pre-calculus, or do you wish I would never bring up pre-calculus?
It's not really a pre-calculus.
Too bad, I am right now. That wasn't an open call for requests, by the way, so that was a deal with it. Do you remember what you would do to graph this? You have to figure out end behavior, for example. Don't worry about that. End behavior, what is that in calculus known as? End behavior. What the hell? End behavior? Do you guys know end behavior? You ever heard that terminology before, end behavior?
Yes.
All right. It's what the function does
At the end.
at the end. It's crazy. What are you going to call this behavior? So this one would look like what? It would look cubish, right? It would look like that. Because it's an odd power at the end of the day, right? If you multiply it all, you get x to the fifth as your highest power. All right, but that's limit as x goes to infinity and negative infinity. That's what that is. Now, what else did you do? You looked at what this thing was doing. Where was it positive? Where was it negative? I don't know if you guys did this, maybe, but you should have. And didn't you plug in here? What are the important points about this? Where it is 0. So 1 and negative 3. Those are where it's 0, right? And then did you plug stuff in to investigate it? And maybe you talked about multiplicity. You ever talk about multiplicity?
Yeah.
Yes? Yes? It's okay to say no.
No.
Or do something. You were in my class, weren't you?
Yeah. 110.
110, all right. I keep forgetting. I knew you were in one of my classes. Let's see. So let's just do this real quick. So you would plug a 0 in. What would you be interested in? What do you want to see? Who remembers this? You want to see the sign. I like it. So you know it goes through 0 at negative 3 and 1. You know it goes through 0. So what you're investigating now is, what is it? Where is it above the x-axis? Where is it below the x-axis? Well, you know, you never said this. You never said this function is continuous. Maybe your teacher did, but normally not. That's why we're able to do this. If it is, when I plug a 0 in, what do I get? You get positive, don't you? Yeah. So it's positive everywhere in there. If I plug in negative 4, what do I get? Positive. That's always positive, right? Negative. So it's negative back here. So if it's negative at negative 4 and it's positive at 0, there's got to be a place where it goes through the x-axis in the middle, isn't there?
Yes.
So we sort of use this idea backwards in a way. We knew it went through 0, so maybe it's on alternate sides around it. Now, of course, over here, it's going to just stay positive over there, isn't it?
Yes.
Because of the multiplicity, or just plug in a 4 or whatever. So it's going to be positive. So it stays positive on that side. but I really want you to get this. So what's an immediate use of the intermediate value theorem? Well, if I know that a function, for example, let's see, blah, blah, blah. I'll take one right out of the homework. Blah, 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 blah. Blah, 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 blah. Here, beautiful. So if I have a function, x to the fourth plus x minus 3, can you show me there's a root? And you're okay with the word root, right? What's another name for the word root? Zero. What's another name for the word zero? The what of the graph? X-intercept. Right, so that's x-intercepts. Show me there's an x-intercept in 1 to 2. Well, now you have a very easy way to do that with the intermediate value theorem. Let's see if you guys get this. In order for one way to show there's a root. So obviously this won't show all roots, because what's true about this root? Does it change sign around it? No. So this intermediate value theorem, though, it can pick up roots where it does change sign. So you're guaranteed there's a root in between them if the function evaluated at one of them, the function evaluated at the other, are different signs. So what is f of 1? And what is f? Yeah, 1 plus 1 minus 3. What's f of 2? So it's negative here and it's positive there. Therefore, somewhere between 1 and 2, because of the intermediate value theorem, somewhere between 1 and 2 there must be a place where the function has an output of 0 in between those. Yes, sir?
Does 1, 2 stand for a point or a...
No. The interval notation sucks so hard because we had points before we had that.
Yeah.
So whoever invented that should have come up with a better thing. I should say in or on. So you got to take it out of context. On this interval. So when I say like on 1, 2, that's an interval.
Okay.
I like it. Now when it's got the brackets, it's easy to tell.
Yeah, okay.
Yeah. How we doing? So be really careful. You got to look at context to see, is it a point they're talking about, or is it an interval they're talking about? It so sucks. Okay. Cool. Oh, good. All right. I got time for this. Let's see. I think that's it for section 2.5. So section 2.5 is all about continuity, what it means, what types of functions are continuous, and then our first major theorem is the intermediate value theorem, which at the end of the day is we can almost call it the duh theorem, right? All right. So here's the last thing we'll talk about today. I want to talk about this because I think it's going to help us when we go back to section 2.4, because this makes a lot of sense. I feel like it's a scene from Princess Bride where you're like, I don't know if you know what that word means. But inconceivable. I do not think you know what that means. There we go. Okay. So this is the visual of what I tried to say the other day. If there's a limit when the x goes to infinity, what does that mean? So where was one example? So sine. Why was sine the limit as x goes to infinity of sine of x? Why does that not exist? Say again? It's oscillating. So in order for a limit as x goes to infinity to exist, in order for that limit to exist, here's the formal definition of that. If you give me, so if I said, I love this function here, the limit become an IM as x goes to infinity of e to the negative x, let's say x e to the negative x, I like it. And I'm claiming that that's equal to 0. That must mean that if you give me some arbitrarily small number, then I have to tell you some value of x that this will always be smaller than that number you gave me. Does that make sense? If I claim that this limit is 0, at some point it's got to get so close to 0 and it never gets far away again. So if this function did this, it looks like it's going to 0, right? It's like, I'm going to 0, and then it goes, no, I'm not. No. So if you tell me some epsilon, that's what we normally use for very small numbers, is this E, that weird looking E, that's epsilon. So when you say epsilon greater than 0, what that's really saying is some arbitrarily small number. So see up here? That's not very small, but relative to other numbers, that's relatively small, right? If you give me some epsilon, I have to be able to tell you some number after which my function is always closer than that to the limit. Let me say that again. I really want this to make sense. So if you give me some epsilon, so this limit looks to be 3. So you give me some epsilon, so let's say you say, I want you to be 0.13. So is this m good enough? Is it always closer than that distance to the limit? I think it is. How far away from 3 could it get? Does it get outside of this much? You're telling me, I gave you this epsilon. I want you to be at most that far away. If it is the limit, you should be able to do that. It's supposed to get really stupid close. That's what it means to have a limit. It's supposed to be really close and never far away again. Keep getting closer. So is that m good enough? No, it gets farther away than I'm supposed to. But isn't there a point where that little purple line is fully contained?
Yes.
Yes, that's the idea. And of course, they didn't go far enough maybe. If you give me epsilon of 0.00001, well, the amplitude is going to keep going smaller and smaller and smaller, right? So a more interesting function than this would be, I don't know if you guys have ever seen this. You should have seen this. That is basically that if I add 3 to it, right? And if you ever plucked a guitar string, has anybody ever plucked a guitar string ever? Thank God it's damped, or else any guitar string ever plucked would never stop going, right? But the oscillations, the frequency, the oscillations go down, 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 and eventually they just die out.
Yes.
Thank the gods. Theoretically, it would keep going forever, but it's quantized. It's not going to do that, right? So thankfully, eventually it's going to die.